many very important articles on, hopefully you'll tell us about some of the results, about extremal set systems. The title is os-Ko-Rado and
theorem, yeah.
And beyond. Yes.
Muito obrigado. Desculpe-me, eu não posso falar em português. So I have to speak in... I could try and speak in Spanish, but probably it's still better I speak in English. I will write more as Rob has proposed. So actually for many people in Hungary and also for myself, it's this year is an important year because this is the year where Professor Erdös, if he was alive, would be 100 years old. So you can see actually an advertisement for the big celebration in Hungary this July. I will go also. And he was definitely the person who influenced my life most because I know that many of you are high school students. I have been also on the Hungarian national team on the International Mathematical Olympiads and got a gold medal, and then, of course, went to university to study mathematics and didn't much think about becoming someone in combinatorics. But then I saw Erdös, and he kind of changed my way of thinking. You, of course, you haven't seen him, but for me, for many reasons, he was a very important person. First of all, for him, it didn't matter whether you were a young student or a very established mathematician. He would relate to everyone in the same way. So you could be a high school student and write him a letter. Those days, there was no email. And he would definitely write you an answer. And if you asked him about a problem, he would tell you a problem. So he was something really very special. And so he did get me into this field of mathematics. And how actually I got into this field? Actually, it was a student of him, now a friend of mine, and even he was my teacher. He was Katona. And he had a seminar on this extremal set theory. So at universities, people have seminars, and it's all seminars are advertised in, say, September, and you would put out a board and say that in this seminar we are going to teach about, I don't know, hyperbolic geometry or dynamical systems or whatsoever, make some detailed things. But in Katona's advertisement was the following, that suppose that you have a finite set, say X, and you have a family. I will use this word very often for a collection of subsets. So it's F is F1, F2, F sub M. Each of these Fi is a subset of X. And suppose further that for all I and J, Fi intersection Fj is non-empty. Prove that M is less than equal 2 to the n minus 1. And then below it was written, if you can solve this problem, then please come to the seminar. So I like very much problems, and I looked at it, thought about it, and after some consideration I could solve it. So I was an honest young guy, so I said I should go to his seminar. And then that's how I actually started to get into this field of mathematics. And still I must say that what I am most attracted by it is the simplicity of the problem somehow. we all know the name of Wiles, who solved the Fermat's conjecture, and about the a to the n plus b to the n not equal c to the n. I mean, that it never had a solution for n equals 3. And he got into mathematics, and he always wanted to solve it, but he got interested by this problem when he was still in high school. So I do believe that it's important for mathematics to have some problems which you can state in 3 lines or sometimes even less than that, and people like intelligent high school students would be able to understand it. Of course, they couldn't solve it. It took more than 20 years even for such a genius like Wiles to solve that Fermat's problem. And many of the people who thought about some problem and wanted to solve it as a high school student, they never even got to that problem later, and they changed their direction. But still, I am personally even now very much attracted to problems which you have to show something with few conditions, understandable conditions, and if possible with really non-trivial proofs. Now, I will tell you the proof for this one if you didn't have it yet. It's really a very simple proof. There are actually several proofs, several ways of telling it, but the main idea is actually the following: that if you look at this number 2 to the n minus 1, it is just 2 to the n divided by 2. That means that what you want to show, that you can have at most half of all the subsets if you impose this condition. Now, it's very easy to see that if you have if you want like pictures and you have here your ground set X, and you take an arbitrary subset, say A, then whatever remains is the complement of A, so that's the usual terminology, so it's X take away A. And it's clear that these two sets are in one-to-one relation to each other. The complement of A complement is A again. And out of these two sets, there could be only one of which is in your family. Because no need to say, you can see it even from my picture, that this is, their intersection is the empty set. So it's not hard to divide your family into 2 to the n minus 1 pairs, each of them consisting of a set and its complement, and therefore you couldn't have more than that much. Or if you want to write it in another way, I will erase it straight after so that I will have more space to write. If I write down a list of my sets, and just next to it I write down their complements, then I can claim that all these altogether 2m sets are distinct. So I never wrote the same set twice. Why not? Because this that's exactly what I said. If, say, fi was the same as the complement of some fj, that would exactly mean that fj is the complement of fi, and these two sets have empty intersection, which is not permitted. So therefore 2m, they are all distinct, they are all together 2 to the n subsets, so we get the inequality m is less than half, 2 to the n divided by 2. Actually, this very simple result occurred in one of the first papers in extremal set theory, a paper written by Erdös, a Chinese person who was in England before the war, and Richard Rado, who is a German person who moved to England out of fascist Germany, and so they worked together in England, and Erdös told me that it was around 1938 that they got this result. They didn't publish the paper. Their paper got published only in 1961. Well, it's not that the backlogs were so long those days. It was just that combinatorics was very, very far from general interest, and they had some results, but somehow they didn't bother about writing them up. And later, it was much after the war, Erdös spent the war at Princeton, but after the war he was traveling a lot. He often went to visit his friend Richard Rado, who was at the University of Reading, and so they did some other work, and at some point they decided that combinatorics is already considered to be a field of mathematics, not just a field of interesting problems. So they wrote up the result. And it was not this result. Their paper contains some, what is really called the Erdös-Ko-Rado theorem, and I am going to state it to you. It will be very much the same condition, the main difference being that you are not going to look at subsets without any restrictions, but you are fixing an integer k, where this integer is at least 1 and less than or equal to n over 2. And you impose the same condition that you have this family of sets, and I will use this notation, which is now very common, this binomial coefficient, but no number, but a set on the top. This denotes all the k subsets. So you have a family of k element subsets, each of them has k elements, and the condition is still the same, that f intersection f prime should never be the empty set. Well, if you think about it a second, then you understand that why we need this condition that k is less than n-half, because if you have sets which are size more than n-half, then it will be automatically satisfied. Any two sets of size more than n-half will have a non-trivial intersection. So you couldn't get any interesting bounds, but Erdös-Ko-Rado proved that in this case, that k is at most n-half, you can never have more than n minus 1 choose k minus 1 sets. So this is what is usually called the Erdös-Ko-Rado theorem. So what is this bound coming from? Well, you take just fix one element, say the element lowercase x, and take the family, I just call it f sub 0, such that so all the k elements sets which contain this fixed element. Well, one thing you see certainly is that since all subsets contain this x, the intersection of any 2, any 3, any 100 of them even is containing also this element. So you won't get empty intersections. And also, it is obvious that f sub 0 has size n minus 1, choose k minus 1. Well, we have got a result, it is best possible, so is now everything finished? Well, not quite. Actually, one of the things Erdös liked probably most is whenever he saw a theorem or a statement, he tried to generalize it. Whether you want English or American spelling, I don't know. On my computer, if you write center in the good old British way, it would always get a red line on the bottom showing that this is not the correct pronunciation because it's done by either Apple or by Microsoft, both big American companies. I have a French citizenship, so I personally I prefer the good old spelling, but I don't like to see all those red lines. So in mathematical papers, I stick to that one. But anyways, so he likes to generalize. So what can we generalize it? And the first thing you can generalize is this, that, and I will give you the definition of t-intercept. So what is t-intersecting? Here you have a number 1 less than or equal to t. In our case, it will be less than or equal to k. And you say that the family f is t-intersecting if f intersection f prime has size at least t. So the original Erdős-Rado theorem is about one intersecting families. Any two sets have to have intersection at least size 1. So and what if you have at least t? Well, and that is this second half of Erdős-Rado's paper. They prove that if subject to this condition and the other non-trivial condition that n should be at least some n sub 0, a function of k and t. So, and in their bound, n is really very big with respect to k and t, something like exponential. In that case, you couldn't do better than take all the t-element subsets that contain a given fixed t-element subset. So in this case, this f0 would be, instead of taking it this way, but you would take say A is contained in F, where A is a t-element subset. And then the size of your family would be n minus t, choose k minus t. Well, one of my early results when I was still a student, I basically determined what this function is. Namely, I showed that, at least I could show it for t at least 15, that this inequality, let's give it a name, star. So the star, t is a number at least 15 fixed. The star holds if and only if n is at least k minus t plus 1 times t plus 1. You note that if you put t equals 1 here, you will get k times 2, which is just what is in the original Erdős-Rado theorem. I had it written in the other way. So it's only some linear function of k, almost just t plus 1 times k, slightly less. And I use it with purely combinatorial methods, and then Richard Wilson, he gave an algebraic proof which works for all t. So we know that this is true for all t, at least 1. That was using some eigenvalues of some related matrices. But anyways, that's pretty much now, for that we know what is happening with the Erdős-Rado theorem. And now I'm almost, time-wise, I'm close to halfway to my proof, so not proof, but lecture, so I think that I should get yourself a little bit more relaxed, or at least. So I wanted to bring more juggling stuff to Rio, but I only brought a small bag, so I could only fit in my balls. But I must say that I can say in some sense that I owe my juggling to Paul Erdös, because when Paul Erdös was 60, it was in 1973, you can count, take away 40 years from now. Then at that time, there was a big conference in Hungary, and that was the very first mathematical meeting I went to. And there was also Ronald Graham, who is a great combinatorialist, but also he's a past president of the American Mathematical Society. Are they bound together? It's a rope. And he taught me juggling 3 balls at that conference of Paul Erdös. And that changed my life in another way. So there are many, many ways you can do it with 3 balls. That is called a shower. Look at the white one. It is too lazy to go up. Oop. It went down a little too fast. Yep. Where is the ball? I can't see it. So I will show you the Argentine way of juggling, okay? How the people in Argentina juggle. I'm sure that you can go home and try it yourself. If you just put it right and let your hand, your arm move a little bit, it will just fall out into your hand. So, but anyways, I will maybe do some more juggling later. Let's get to work, back to work. And so on the other part, extreme of the blackboard, I'm not sure whether we can call it, it's rather a green board, I would say, rather than black, but I would write a problem which is, it almost looks like an Olympiad problem. So let us look at the numbers x1, x2, x sub n. They're all real numbers. And actually, we suppose that they sum up to 1. Sum up to 0. Well, what you are interested in is to look at this for some fixed k. K is fixed. And you are looking at subset sums. So I can write it like this. xi sub 1 plus xi sub 2 xi sub k. Where, to make it precise, I sub 1 is less than I sub 2, less than I sub k. What you are interested in is that how many of these sums will be non-negative? Well, there have to be some that are non-negative, because if you would add up all these n choose k subset sums, you will see that it's just a constant multiple of the sum of x1 up to xn, which is 0, so some have to be non-negative. Well, there is a pretty natural construction to give relatively few subset sums is the following. Take x1 equals x2 equals x sub n minus 1 equal minus 1. And just let xn be n minus 1. So it's only xn that is positive, and all the others are -1. That definitely verifies the condition that summing all of them is 0. But how can you get a non-negative sum? The only way to get a non-negative sum is by taking k elements. I mean, the last one, the ik has to be, this will be non-negative for this construction if I sub k is n. So if you add negative numbers, no way you are going to get a non-negative sum. So you have to use the only positive member. And how many subset sum does it give? It gives you n minus 1 choose k minus 1. Actually, I won't go into details for n equals some, say, yes, n equals 3k plus 1. There is some construction, not quite trivial, for which actually you get less than that many subset sums. But now the general conjecture, which is due to Manikam and Miklós and Singhi, these two people being Indian and he's Hungarian, and they conjecture that for n at least 4k, this number is the minimum. So at least this many subset sums are always non-negative. No matter how you take your n real numbers, if they add up to 0, then at least there are n minus 1 choose k minus 1 choices of k of them which add up to a non-negative number. And now what I'm going to show you is, and that was in the paper of Manikam and Singhi, and they are building on an argument which is a special case of an argument used by Katona. So I'm going to give you a common proof of this statement and their statement, which I didn't state yet. I'm stating it now. So Manikam and Singhi, they proved it if k is a divisor of n. So if k is, so n is a multiple of k, then they could show, and you will see the argument will be pretty simple, that you can have at least n minus 1 choose k minus 1 k element subsets. And also, I will give you I'll show you that the same proof, and that's what was there earlier. This case of the Erdős, so the original Erdős theorem for t equals 1 intersecting family. So what is the idea? The idea will be very much simple, like this idea here. That if you had two sets that were pairwise disjoint, then, of course, you couldn't have both of them in intersecting family. So let us now consider, to make these two things together, which might be not the best idea, but nevertheless I'm sticking to that. Let's fix this n element set to be the first n integers. And I want to make a definition. Instead of writing so many subscripts, I will take a k-element subset of the integers up till 1n, and I will denote by x sub f, this is a pretty common notation, as the sum of x sub I, where the summation is over all elements of f. So I just, instead of writing this double indices, I tell you what are those indices by this set. And now, let us so as I told you, I'm going to deal now with the case when n is a multiple of k, so say n is a times k, a is an integer, at least 2, and I'm looking at a partition x equals f sub 1, f sub a, each of the fi having size k, and for 1 less than equal I, less than j, less than equal a, fi sub f sub j intersection is empty. If I want to fit it into this, my only picture so far, then you would have A1, A2, A3, no, not A, I'm sorry, F. So you just take a partition. Well, what can you say? And I'm going to say it in both cases. Well, for the Erdős-Korádó theorem, so suppose you have a family of k-element subsets, no two having empty intersection, then at most one of these sets can be in the family. Since any two intersect trivially, only in the empty set. So out of this A sets, no two are in F. So out of these A sets, at most one will be in your family. I will probably give another argument, but simple averaging would show from that the size of F is at most n is, remember that n is a times k, so F is at most a over 1 over a times a k choose k, which is exactly a k minus 1 choose k minus 1. I still have to say something about this averaging argument, which I will do, but before that, let's apply the same argument to the subset sums. Well, if we have a partition of all the sets, partition of the ground set X into A sets, then obviously X f sub 1 plus X f sub 2 plus, and you add up all A of them, X f sub A, here you have all the indices from 1 to n. So this is absolutely the same as x1 plus xn, which we know it is 0. So here you have A subset sums whose sum is 0. That shows that at least one of this f sub I satisfies that x f sub I is at least 0. So here you got the opposite thing, that for this number of subset sums, so number of non-negative k sums, that means k-element subsets, is at least a proportion 1 over a times a k choose k, which is a k minus 1 choose k minus 1. So what about this averaging argument? The averaging argument would be that if you would take a random partition, then how many of these sets would be in your family? Well, if you take it randomly, then the expected number will be just exactly this a times the size of your family divided by n choose k. And we know that this would be the expectation, and since at most one of them is in the family, you have this is at most 1, which is exactly the same as saying that f is at most that much, and you would get a result. There's another way of going around it, and that is you can use a much deeper result that you can partition all the n-element subsets, all the k-element subsets of this A times k-element set into partitions of perfectly. It's a nice theorem of Baranyai, a Hungarian mathematician who unfortunately died young in a car accident. But in any case, that's thinking of time, I'm going to skip telling it in detail, but the big difference is that some extension of this easy argument was done by Katona, and that worked for all n. So for all n, one could get for that simple proof of the Erdős-Kradó theorem. However, for 30 years, not much happened with this Manica-Miklós-Szingi conjecture. They had a paper in which they proved that that instead of this 4k, some super exponential bounds more than k to the k's power, it is still true. And I want to sketch you a proof which I found.
Peter?
Yes.
I think some of the people may not know what expected value is, so perhaps it's just worth mentioning that what you did here was very similar to what you did at the very beginning.
Yes.
But the argument is very similar.
Yeah.
It's expressed in a nice language. It's almost the same. And okay, using this clever factor theorem.
Yeah. So what do we know actually now? Nowadays, the best bound actually known for this is that it is true for n at least 33 times k squared. And that's a result due to Alon, Howe, and Sudakov. Just appeared in the beginning of this year. And they have actually used some Erdős-Kradó type theorem also in their proof. And what I could actually do, I couldn't do better. I proved this same for about n 2 times k cubed, but with a very simple argument which I kind of try and sketch you in the remaining time. And that's how we go. So let's order the elements. Well, I had here xn equals was the largest, forget it, and it doesn't matter, it could be, see. Let's have it that way. X1 is, they're ordered increasingly. And the proof is going to be in several steps. In a sense, it will be some process of taking out negative sums. That's what we are going to do. We first look at the element xn and check whether there exists some set f. So this a k-element subset, of course, such that the corresponding subset that n is in this set, and the corresponding subset sum is negative. So you have seen that the example of Manica and Szingi, that was that all the sets where there were very few k subsets summing up to a non-negative number was when there was only those which contain the element xn. So that's kind of checking what is the situation. So you look at the subset sums containing xn. If all of them are non-negative, we have nothing to do. They are n minus 1, choose k minus 1 of them. And that will be the only case of equality. So without loss of generality, we assume that there is some subset f, n is in this subset, and the sum of, actually without, with this ordering, I can just say that all the other members of the same will be true even if I take x equals 1, 2, k minus 1, take the smallest k minus 1 and then add the biggest one to them. So this will give you a negative sum. So what do I check next? Well, not surprisingly, next I will check, and I can say it in this formal way also, for x sub n minus 1. So I found it negative, and now I am checking whether the sum for x starting with k, x sub 2k minus 2, and add to it x sub n minus 1, and I check whether it is positive or negative. Well, again, there are only two possibilities, either positive or non-negative. So if it is non-negative, what can I say? Well, we had the first k elements, k minus 1 elements, and I took the next k minus 1 elements. And here we are at the very, very end. And actually this is a long thing because we have 2 times k cubed sets. Here we have x sub n, so n minus 1 and n minus n. And we checked that whenever we use xn minus 1 together with the worst possible, the smallest possible k minus 1 elements, we get a non-negative sum. What does it mean? It means that not just this, but I could take any other n minus 1 element subset from there and still get a non-negative sum. So how much would it give? Well, not as much as we first would like. It would we take the element n minus 1, and out of this n minus k minus 1 elements, you can take the remaining k minus 1. Well, you will say that that's not enough. Indeed, it is not enough. It is just n minus k minus 1 choose k minus 1, which is considerably smaller than n minus 1 choose k minus 1. But on the other hand, for each of these sums, I can replace x sub n minus 1 by the x sub n, which is at least as large as x sub n minus 1. We had them in increasing order written here. And that will also give you a non-negative sum. So you can get actually twice as much. And this is, for this choice of n, actually already for k squared, it is, with simple calculation shows that this is really more than n minus 1 choose k minus 1. Well, and what you do, you repeat this argument k times. So then you, okay, so if we had this sum non-negative, then actually computation showed that we have got what we wanted. And then we go on. Look at the next smallest k minus 1 elements here, so k minus 1 of them, and take out the element x sub n minus 2. So if I look at the indices, it will be n minus 2. And I look at it, and then I would get something like 3 times n minus 2 k minus 1 over k minus 1, which is also n minus 1 minus k minus 1. So whenever if I would end up finding that all the sub-k element subset sums which contain that last element are non-negative, then somehow I get out of the game, I can show you that we have enough of these sets. But at some point I have to stop it. And I basically stop it after k times. So I went as far as I took out the numbers and I went down k times. So I got here until x sub n minus k plus 1. And I had k times k minus 1 of the sets, of the elements here. And in the remaining, for the remaining, I'm not going to repeat this argument. I still have how many sets? I still have there n minus k square elements left, if this process didn't stop. And now I'm going to say something more about it. I'm going to use the simple argument of Katona and...
n minus k cubed.
No,
N minus k squared.
I did it k times. And this is, of course, if this was a multiple of k, I didn't have to start the whole argument, because that would mean that n is a multiple of k. But I take away a few elements, so I can take a subset of, take away a few elements from here, such that the remaining will be a multiple of k. So I just throw away some elements among these negative numbers, the small numbers, namely the elements. How many? Well, if you want to have a formula, it is n minus k squared divided by k, integer part multiplied by k, and take this away from n minus k. Yeah, so this is the number of elements you are going to throw away. So the number of elements you are going to get is n minus k squared divided by k times k. So this is a multiple of k. I look at a partition again, which is, of course, it's going like this, and this is going like this, but a partition of now this index set, I will look at it. Name it by y, and I look at a partition of y into subsets f sub 1, f sub this number, n minus k squared, choose k. I got it almost right. It is almost what I wrote. It's actually, I'm looking, this is a partition of not y, but this is a partition of y union x sub n minus k plus 1 x sub n. I speak about indices, so it's n minus k plus 1 n. So sorry for having made a mistake. So I take these sets and all the last k elements, the big ones. I don't want to miss the big ones. I want to have big sums. So I want to take those numbers which are relatively large. So I put those things back into here. So therefore it is, actually I have this plus 1. And what I claim now, that if I have a partition of this set into k element subsets, what we know before, we know that at least one of the sets will have a positive sum. Don't forget, we took away the smallest numbers. So still, the remaining numbers, if you sum them, that will be non-negative. But I claim that now you have at least 2 non-negative sums. I will leave that as an exercise for you to verify. It is just very simple. It is just using the fact that from all these negative sums, I have thrown away the negative part and kept the positive part. So it couldn't be that just one sum is positive, because even if you had one sum positive, it could not be more than x sub n plus x sub n minus 1 plus x sub n minus k plus 1. That would be the absolute maximum to have that one on one particular set. But even with that, the remaining will be non-negative. So even then you would have one more non-negative sum. So that gives you at least 2 non-negative sums. And since we have this argument that basically will give us for now that at least 2 times, using the fact that it's at least the remaining is at most k minus 1, so you can see that n minus k squared choose k minus 1. At least this many sets, and you verify the inequality that basically for n at least 2 times k cubed, this number will be still above what we want, namely n minus 1 choose k minus 1. And that will be the end of the proof, and more at the end of my lecture. I think I show you some juggling. There are all ways of juggling. There is part which is called contact juggling, where you kind of don't throw the balls but move them around. The good thing about that you can practice them in a traffic jam. I did practice it in movie theaters, but once I dropped the ball and had a hard time finding it in the dark. Balls tend to roll about. So let me do it some opposite juggling too. Let's really. This is less tiring because you don't throw the ball so far high. I must say that you have a very nice floor here. But obviously the most natural juggling is which has been around for more than 2,000 years, is throwing the balls up in the air. And if you think that my lecture is over, then you are wrong. I just want to give you a problem because I didn't give you open problems, and since you are young. And this is my problem which I came upon in 1979 around Christmas, which I spent in Montreal. And it would have helped in some other problem which was not so important, but the conjecture which occurred to me is the following. It's very simple to state. That's why actually it's very popular. Over 100 papers were written about it. Not that anyone found a solution yet. And this is the following. You have a family of subsets, F. So all of the n elements, subsets of the n element set, say at least 2 elements. And the family is union closed, which I give you the definition. It means that whenever set F and F prime are in the family, then so is their union. And my harmless looking conjecture is that you can always find an element of x in the big set such that x is contained in at least half of the sets. So half of the members of this family, if you choose this element x right, then at least half of the members of F will contain it.
Exists.
Hmm?
You wrote for Paul, but many exist.
Oh, yes. It would be even true for the average element. So the average degree need not to be so big. It can be arbitrarily small. There are various results about that also, but the conjecture itself is just this. And if you let me, I tell you that many of you know the name of Ulam, who is a great Polish mathematician who was working on the Manhattan Project along with von Neumann and Teller and people to make the first atomic bomb. And I only met him once. It was in 1981 or 1982 in New York. He was visiting at Rockefeller University, and he asked me, what did I do? And I told him that I'm working in combinatories. And he said that, oh, I just heard a very nice problem. And I thought, okay, please tell me. And then he told me my conjecture. It was really my conjecture. I first told it to Ron Graham, and he told it many people, and it went around, and this famous mathematician, Ulam, who is now considered more than Teller, the father of the hydrogen bomb, that it's not clear whether it was a good invention or a bad invention. We can't be sure. But in any case, he seems to have had the main idea how to make it work. I mean, how can you make it explode? This Ulam, he told me, and it was just my conjecture. I felt very happy about it. So now really my time is over. So thank you very much. Yes.
Is there some known result about the proportion less than 1/2?
So there is no positive